Hi, my name is Rens, and I'm a UI frameworks engineer. Lazy stacks are an essential component for any SwiftUI app showing long and custom scrolling content. And they have long been a part of SwiftUI. Like many other SwiftUI components, the power of lazy stacks comes from their simplicity. Different SwiftUI components can be mixed with many other SwiftUI components to build complex apps. For example, from the 2027 releases, you can use reorderable to drag and reorder views. You can learn more about that in Code Along, build powerful drag and drop in SwiftUI. And SwiftUI allows swipe actions to be added on views outside list. Of course, both work great when used with lazy stacks. I think it's a good time for a refresh and dive into lazy stacks and scrolling. I'll explain how they work, what you can do with them, and what you may want to avoid. Afterwards, you'll have a better understanding of the internals of lazy stacks that you'll be able to apply to lazy stacks in your own apps. This video will assume basic familiarity with SwiftUI layout using stacks. If you're new to SwiftUI, I recommend stacks, grids, and outlines in SwiftUI. I've been working on an origami app that shows the instructions to make some popular origami pieces. In this early version, it's only showing the steps to make a swan. Here's the setup for the main view. I have a scroll view with a LazyVStack inside that in turn contains a step view for each step. The LazyStack allows scrolling through a potentially large number of steps without loading all views at once immediately. I'll now focus on the LazyVStack. 3 of the steps to create an origami swan are fully visible. A small part of the step view for step 4 is also visible. Now, the full LazyVStack is a lot larger than the visible views. But unlike a VStack, a LazyVStack does not evaluate or render views that aren't visible. A LazyVStack simply lays out its views top to bottom and stops once the visible rect is filled. If you scroll down, the LazyVStack adds views as appropriate to make sure the visible rect remains filled. And as views are scrolled out of screen, they're removed from the LazyStack. By not loading all views at once, a LazyVStack can be more efficient than a VStack. But there is a correctness cost. Since a LazyVStack doesn't load all of its views, the height of the subviews that are off-screen are estimated. This estimated height is based on the average size of views that have been placed before and the estimated number of remaining subviews. The LazyStack is also unaware of changes in off-screen views, since they aren't loaded. Similarly, since not all views are loaded, it wouldn't be able to find the maximum width of all views. So the ideal width of a LazyVStack is that of its first subview. In the case of my origami app, the first view is infinitely flexible, so the width of the LazyVStack equals the screen width. Since the height of the LazyVStack is estimated and not precise, it can change during scrolling as the LazyStack learns more about the layout of new views scrolled onto screen. For example, if you scroll down all the way and the last views are a bit smaller than the other views, the LazyStack has to adjust its originally estimated size to account for this. The space above the visible rect isn't precise either. The scroll position, or content offset of the scroll view, therefore depends on an estimated position of the visible items. One example where the space above the visible region is not precise is after an orientation change on an iPhone. Step views are less tall in landscape than they are in portrait. The subtitle text generally fits on fewer lines in landscape. During the orientation change, the LazyStack will keep the step view for step 4, the topmost visible view, anchored. The LazyVStack isn't yet aware of the exact layout changes in the first few subviews, since they aren't loaded. But when scrolling all the way back up, the LazyStack must align to the top of the scroll view. This means it must correct the estimated space above the visible region along the way. It will update the content offset of the scroll view with the same amount, such that the content offset at the top is 0 as well. The LazyStack and the embedding scroll view coordinate the position and content offset. That way, when the estimations are updated, the relative position of the visible subviews in the scroll view doesn't change. It's common to compose different types of views or content in the same LazyStack. For my origami app, I think it could be cool if people could share a photo of their creation with others when they are done. I'd like to display these photos at the bottom in a horizontal scroll view. I've added a showcase view for these photos. The showcase view has the horizontally scrolling scroll view with a LazyHStack within. This means that my app now has a LazyHStack nested inside the outer LazyVStack. Nesting a LazyHStack in a LazyVStack like this can also be good for performance, since not everyone will scroll this nested scroll view to see the extra views. For a LazyHStack, the ideal height, and therefore its height in a vertical scroll view, is that of the first subview. For my origami app, all photos use the same height. But if every photo had a user description label with a variable number of lines, longer subtitles would be cut off. The LazyHStack cannot know in advance what the largest subtitle of all views is. It hasn't loaded all of them. The best solution is to fix the view heights. For example, for text, you can set a line limit and reserve space for shorter text. But I'm actually thinking the photos in my origami app should be a bit larger. Maybe I should just add them vertically below the steps. If I add them in a section, I could even pin the section header. To pin section headers, use the pinned views parameter on the LazyVStack. I've added the new section inside the showcase view with a header view. If I scroll down, the showcase section header sticks to the top. I'll now discuss some patterns to avoid, so the LazyStacks perform at their best. I'll do that using the photos showcase I've just added. It could be nice to add a scroll transition to the photos as they scroll into and out of screen. Here, I'm using the scroll transition modifier to give my steps an effect as they scroll on or off screen. However, LazyStacks only load views that are on screen based on their original position. And the transform here is pushing them out of their original frame. That causes them to disappear when they should be visible, since the LazyStack believes they're off screen. Here, as you scroll down, the pink swan disappears too soon. If you apply a scroll transition to views in a LazyStack, make sure that views that wouldn't normally be visible aren't pushed into the visible rect. Here, I'm using a different scale effect. This works fine. In general, make sure that views that wouldn't normally be visible aren't pushed into the visible rect in a transform. The LazyStack won't be aware of that. Since you need to scroll down a little to get to the showcase, I will also add a button to quickly scroll there. But the button shouldn't always be visible. I'd like it to only be visible when near the top of the scroll view. When someone scrolls down, it should disappear. Here, I'm using an on-scroll geometry change on my scroll view to get the absolute content offset. When I'm scrolled down more than 100 points, the button disappears. This works, but since the content offset of a LazyStack is estimated, the exact position where the button disappears can change when the estimations change. Instead, it's better to use the relative positions of subviews in the visible region of the scroll view. One way to do that is to use the on-scroll target visibility change modifier. The closure in that modifier is called when the visibility of the subviews in the visible region of the scroll view changes. Here, the visibility of the Scroll to Showcase button depends only on which subviews are visible, with a threshold of 80%. I've now covered the layout of LazyStacks in detail. I've said that LazyStacks add subviews when they're about to enter the visible part of the scroll view. However, the subviews a LazyStack loads individually do not always correspond directly to the view structs you define in code. Let's go back to my original code and take another look at the content view. In this simple case, there is a one-to-one correspondence of step view instances and the subviews that the LazyVStack sees. There's a scroll view, and the scroll view has a LazyVStack as a subview, and the LazyVStack has the for each as a subview. But of course, the for each isn't just a single view. It's resolved to one step view for every step. And in most cases, these are the subviews that the LazyVStack loads. But here, the step view is slightly more complicated, and that will be important. The body contains two views, step diagram and step instructions at the top level of the body. They're also not embedded in another layout, like a VStack. In this case, LazyVStack still has the for each, which is resolved to a step view for every step. But just like the for each resolves to multiple step views, each step view now resolves to two views as well. The LazyVStack evaluates and loads step diagram and step instructions separately. Of course, step view still needs to be evaluated for the LazyStack to create either of those. Views can also resolve to a dynamic number of views, but that is something you have to watch out for. In this case, step view is using a detail level environment value to check whether it should be visible. The for each, again, resolves to a step view for each step, but each step view now resolves to either one subview or zero subviews. In this case, step 2 isn't visible given the current detail level, but the first and third steps are. That works, and the contents of the step view are loaded lazily, but the step view itself can be kept alive longer than you may expect. That is because a LazyVStack addresses the visible subviews using their index. It now has to keep earlier step views around just in case the detail level environment value changes, because that would affect the indices. In leaf subviews that are created many times in a for each, like step view, avoid creating a dynamic number of subviews. The example where a detail level environment value is used to filter out steps is therefore not a good idea. Say that an unrelated environment value like writing style is used in the contents of the step view body. A change in this environment value can now cause body evaluations for views that are scrolled out of screen, causing unnecessary view updates. The LazyStack also won't release state allocated for the step view. Instead, filter at the data level. If you're using Swift data, use a predicate to filter your query. Here, I'm using the detail level in the predicate. This makes the number of subviews immediately clear to the LazyVStack. It doesn't have to construct views to compute view counts or indices. Note that unwrapping an optional in a view body has the same effect. Here, I'm optionally unwrapping an API token environment variable. The body only returns something if that token isn't nil. The token is something that could be handled by a network client model object. If someone is not authenticated, a view higher up in the hierarchy could show a content unavailable view, instead of showing the LazyStack in the first place. Since LazyStacks only keep a small part of their data in memory, they do not need to perform a full diff of their contents. They only perform a minimal check for changes in the visible views. LazyStacks don't always load a subview all at once. I'll now discuss prefetching, an internal mechanism with which LazyStacks improve the scrolling performance of your apps. When you scroll in a specific direction and the visible part of the LazyStack reaches the end of the placed content, the LazyStack already prefetches views before adding them on screen. Prefetching means that the LazyStacks will perform part of the work of displaying a view before it's visible. While scrolling, a scroll view needs to draw frames at a constant rate. That means there's only a limited time available to perform computations, up to a frame deadline. This work includes the scroll view updating the content offset, your views rendering at a new position, and work your app may do in response to the content offset change. And when the scroll view contains a LazyStack, it includes the work for evaluating views scrolled on screen, performing the layout, and rendering them. But the work for placing new views on screen can be expensive. If the work would take too long passing the deadline, that would result in a dropped frame. That is visible as a hitch while scrolling, so that should be avoided. Prefetching is used to prevent such dropped frames. While scrolling, the LazyStack already checks if there's enough time available to perform part of the work of rendering a new subview before it is scrolled on screen. For example, a LazyStack may be able to evaluate the body and layout of a view about to appear on screen before it appears. When the view finally does appear, most of the work has already been performed, broken up across multiple frames. The work to show a nested LazyHStack in a LazyVStack can be broken up across multiple frames as well. When the view appears, onAppear is called. So generally your view's body is called at one point, and onAppear only a little later when the view is placed on screen. If the scroll direction is reversed, it's even possible that the view's body is called as part of prefetching, and onAppear is never called. Using onAppear in a LazyStack is useful for a number of things, even for data loading. One such use case is infinite scrolling. Here, the Origami app fetches more photos from the web when you scroll down to the end. The last view, a progress view, has an onAppear modifier. When that view appears, a new page is fetched. But loading everything in onAppear for each view is not a good idea. In this example, onAppear is used to set up every view. The size and large parts of the view's contents completely change after it's placed. The work that prefetching has done earlier will be thrown away and has to be redone when the view appears. The LazyStack may also load more views than needed, and scrolling can be affected, as I'll show later. Instead, set up the view in the initializer such that it is in a reasonable state before it appears on screen. Even when it's not essential, it can be useful to load content before views appear. Here, I'm using the task modifier to remotely load a diagram from the internet when the view appears. But I can actually make use of prefetching to load it slightly earlier, so the chance is higher it's loaded by the time it appears. For example, I could use a diagram loader observable object connected to a cache. When the cache doesn't contain the data for a specific ID, it could load the data immediately when it's initialized. Since it starts loading the diagram in the initializer, the diagram will be fetched slightly earlier. Views that are scrolled out of screen aren't rendered or updated anymore, but they aren't removed from memory immediately. LazyStacks keep these around for a number of updates, in case they're scrolled back on screen. When views finally are deleted from memory, state variables are deleted alongside. Since the data associated with views scrolled out of screen will be deleted, don't depend on view state for data that needs to be kept alive after scrolling. Here, StepView uses an isHighlighted state variable. But if the view is scrolled away, that highlight state will be lost. Instead, move important state to model objects, or outer views using binding, as here. You typically use LazyStacks inside a scroll view. I'd now like to give you some tips to make scrolling work well in LazyStacks. Earlier, I added the button to my Origami app to scroll to the showcase with user photos. The code to programmatically scroll to the section would look like this. I'm using a scroll position binding to scroll to the showcase's section header. Programmatic scrolling works in LazyStacks, even if the target view isn't on screen. Scrolling to an off-screen view requires the LazyStack to estimate its position. In an animated scroll, the LazyStack updates this estimated position on every frame. Still, there are some things that can prevent scrolling from being smooth and fast. For example, also here, having a dynamic number of views in StepView has a performance impact. Programmatic scrolling to a view with an ID is most performant if each view in your for-each always resolves to one single subview. In that case, the LazyStack can query the for-each to find the ID to scroll to without constructing any of the views. Scrolling to a subview near the end is also more performant if the LazyStack can quickly count its subviews. As before, instead of filtering out views with the conditional in the view body, you should filter on the data level, for example, with a predicate on a query. Programmatic scrolling also becomes less smooth if too many views change their layout after they appear on screen. A common pattern that does this is using onGeometry change to set a state value that is then used in another layout pass. Here, StepView has a state variable subtitle height updated in an onGeometry change on the subtitle. The view is then evaluated again, and subtitle height is used to compute the frame of the diagram. This makes scrolling less reliable. The LazyStack measures the view's original height, but the height changes after the view appears, pushing down other content. In cases like this, if you cannot use SwiftUI's layout primitives, use a custom layout instead. Here, that custom layout is Step Layout. To learn more about using custom layouts, check out Compose Custom Layouts with SwiftUI. Alright, I've shown you many aspects of LazyStacks. I've talked about their layout, how view structs don't always resolve to a single subview and how that affects LazyStacks, how LazyStacks prefetch views for better scrolling performance, and how they allow programmatic scrolling to views off-screen. Along the way, I've given some tips and best practices that you can use for LazyStacks in your apps. For example, avoid using the absolute content size or content offset with LazyStacks, since these are estimated and unstable. Avoid using conditional view content in leaf views to filter out data, as that can cause SwiftUI views to stay alive longer than expected. Set up your LazyStacks subviews before on appears scope where possible, to ensure prefetching works best. And don't change the layout of subviews of LazyStacks after they appear, as that can push the LazyStack out of the targeted scroll position. Understanding some of the mechanisms with which SwiftUI components work helps you excel at using them. And I think after preparing this video, I now excel at creating swans.